In this video, we're going to focus on Le Chatelier's principle. Now you might be wondering, what is Le Chatelier's principle? What's the basic idea behind it? Well, whenever you impose a change on a system at equilibrium, the system is going to move in such a way as to undo that change or relieve some of that stress that you impose upon a system. So let's say the system is at equilibrium. Let's say this line represents equilibrium. Let's draw a straight line. Now, if you try to, let's say, raise it up, let's say if you bring it up, the system is going to try to bring it back down. If you try to bring it down, it's going to try to bring it back up. Whatever change you impose upon a system, the system is going to try to undo that change. And that's the basic idea behind Le Chatelier's principle. Now let's consider another example, but one that deals with a chemical reaction. So let's say we have reactant A, and it's going to react with B. B is going to be in a gaseous form, and this is going to produce C, which is a gas, and D, which is a liquid. And let's say the coefficients are 1, 2, actually, let's make this 1. We'll make this 2, and this will be 1. Now this chemical reaction is at equilibrium. Equilibrium, with regard to chemistry, when a chemical reaction is in equilibrium, it's not static equilibrium, where everything is stationary. We have a case of dynamic equilibrium. That means things are moving. When we have dynamic equilibrium, the rate of the forward reaction is going to be equal to the rate of the reverse reaction. Because these two reactions are occurring at the same rate, there's not going to be any net change in the amount of product and reactants. So the concentration of the products and reactants, they remain constant at equilibrium because the rate of the forward reaction equals the rate of the reverse reaction. So that's the situation that we have at equilibrium. Now let's consider what's going to happen if we add stress to the system. So let's increase the concentration of reactant B. If we introduce more of substance B to the vessel, if we increase its concentration, what's going to happen to this reaction? Will the reaction shift towards the right, that is towards the products, or will it shift towards the left, towards the reactants? So think of the concept of equilibrium. We're increased in reactant B. According to Le Chatelier's principle, the system is going to try to undo the change that we have just done. So since we've increased reactant B, it's going to do something to decrease reactant B. So in which direction should the reaction shift if we want to decrease reactant B? If the reaction shifts to the right, we know the products will increase. If it shifts to the left, the reactants will increase. Now we want the reactants to decrease, not increase, so it has to shift to the right. Whenever the reaction shifts to the right, the reactants decreases, the products increases. When it shifts to the left, the reactants, they increase, the products, they decrease. So we want the reactant to decrease. Therefore, it's going to shift to the right. Now, what happens if we decrease the concentration of reactant B? Let's say if we remove B from the reaction vessel, what's going to happen now? Well, since we brought B down, according to Le Chatelier's principle, the system is going to try to undo that change. It's going to do the opposite of what you've done to the system. So you brought the level of B down, it's going to try to bring B back up. So B is a reactant. In order to increase the reactants, we need to shift to the left. So if you remove B from the reaction vessel, the system is going to cause the reaction to shift to the left, producing more B. So whatever you do to the system is going to try to undo the change that you impose upon it. Now let's focus on the products. Let's say if we increase the concentration of C. What's going to happen? Will it shift to the right or to the left? Now, C is a product, and if we increase it, the system is going to try to decrease it. In which direction should the reaction shift in order to decrease the concentration of C? Or you could say the partial pressure of C, since it's a gas. If the system were to shift to the right, we know the reactants would go down, the products will go up. C is a product. The system is not trying to increase the product. It wants to decrease it, so it has to shift to the left. Where the reactants would go up, the products will go down. So if you increase C, the system is going to move away from C to decrease it. Whenever the system moves away from a reactant or a product, that product or reactant is going to go down. When the system moves towards it, it's going to go up. So let's say if we were to decrease C, the system is going to try to increase C. In order for the system to increase the concentration of product C, it has to shift towards the products. So it's going to shift towards the right. So to review, if you were to increase the reactants, the reaction is going to shift to the right. If you were to increase the products, the reaction is going to shift to the left. Now, what's going to happen if we increase reactant A? Let's say if we introduce substance A or more of substance A into the reaction vessel. What's going to happen to the reaction? Will it shift to the right or to the left? A is in the solid state. As a result, increase in A will have no effect on the position of equilibrium. The reaction will not shift to the right, nor will it shift to the left. Now, if you recall, the equilibrium constant K is equal to the concentration of the products divided by the concentration of the reactants. Notice that A and D are not included in the equilibrium expression. The equilibrium constant does not depend on the value of A or D because they're in the solid and liquid phase. The only thing that will affect K is gases or substances in the gas phase or substances dissolved in the aqueous phase. So if it's not dissolved in an aqueous solution or if it's not a gas, it's not going to be included in the equilibrium expression. So changing the value of a solid or liquid, it's not going to have any effect on the position of equilibrium. So if we were to increase D, let's say if we were to add more of substance D, this will have no effect on the position of equilibrium. Adding more liquid to the reaction vessel, it's not going to affect these two reactants. It's not going to affect B or C because they're in the gas phase. So they're outside of the liquid. Therefore, to summarize, increasing or decreasing any reactant or product in the solid or liquid phase will have no effect on the position of equilibrium. So just keep that in mind. But now let's go ahead and work on some practice problems. Number 1. Which of the following actions will cause the reaction to shift toward the left? So let's analyze each answer choice. So what's going to happen if we increase the concentration of nitrogen gas? Nitrogen gas is a reactant. If we increase the concentration of the reactant, the system is going to try to undo that change. It's going to try to bring the concentration of N2 back down. And remember, anytime the reaction shifts towards the right, the reactants will go down, the products will go up. If the reaction shifts to the left, the reactants go up, but the products go down. N2 is a reactant, so it's going to go in a direction to decrease that reactant. So it's going to shift towards the right. So thus we can eliminate answer choice A because it's going towards the right. Now what about B? Let's say if we were to remove NH3 from the mixture. So if we're decreasing the concentration of NH3, in what direction will the reaction shift? Well, according to Le Chatelier's principle, we're decreasing the product. The reaction is going to try to increase that product. So in order to increase the product, it has to shift to the right. So we can also eliminate answer choice B since it's going to the right. Now what about C? The addition of a catalyst. If we were to add a catalyst, what's going to happen? Will the reaction shift to the right or to the left? The addition of a catalyst will cause the reaction to speed up. So the reaction is going to go towards equilibrium at a faster rate. A catalyst works by speeding up the rate of the forward reaction, so it's going to increase Kf, but it also increases the rate of the reverse reaction. So the reaction is going to go to the right at a faster rate, but it's also going to go to the left at a faster rate. Thus, it's not going to change the concentration of the products and the reactants. Because the relative concentration of the products and reactants won't change, because there's no net change by introducing the catalyst has no effect on the position of equilibrium. Even though it speeds up the reaction in both ways, it doesn't shift it to the right, nor does it shift it to the left. So it has no effect. So C is out. So remember, a catalyst simply speeds up a chemical reaction. It has no effect on the position of equilibrium. Now what about removing hydrogen gas from the reaction vessel? What's going to happen if we decrease the amount of hydrogen gas by taking it out of the reaction? So hydrogen gas is a reactant. If we decrease the amount of hydrogen gas, the system is going to try to do the opposite. It's going to try to increase. So it's increasing a reactant. Now what must the system do in order to increase the reactant? The only way it can increase the reactant is by shifting to the left. And that's what's going to happen. So if we remove H2, the system is going to try to produce more of H2. Therefore, D is the answer that we're looking for. So that's the action that will cause the reaction to shift towards the left, is by decreasing one of the reactants. Number 2, which of the following actions will cause the concentration of CO to decrease in the reaction vessel? So let's look at each answer choice. If we were to add more CH4 or more methane to the reaction vessel, what's going to happen? As we increase the concentration of the product, the reaction is going to shift to the left. It's going to move away from the product side so as to decrease methane. Remember, if it shifts to the left, that is towards the reactants will go up. It's moving away from the products, so the products will go down. As it shifts to the left, what's going to happen to CO? What will be the effect of CO? Now, CO is a reactant. So when a reaction shifts to the left, CO is going to increase. Methane, being a product, is going to decrease. So since you increase methane, the system is going to try to decrease it. And as it shifts to the left, the effect on CO is that it's going to increase. So since CO is not decreasing, A is not the answer we're looking for. Now what about B? Removing H2 from the reaction vessel. So if we were to decrease the concentration of hydrogen gas, what's going to happen? Hydrogen gas is a reactant. And as you decrease hydrogen, the reaction is going to shift towards it. Remember, the system is going to try to do the opposite of what you did to it. So because you added hydrogen, the system wants to, because you removed hydrogen, the system wants to increase it back to its original level, or at least somewhere closer to its original level. The only way it's going to increase the reactant is by shifting to the left, which is what's going to happen. And as it shifts to the left, the concentration of CO is going to go up again. So B is not the answer we're looking for. It's not going to decrease the concentration of carbon monoxide. Now, what about answer choice C? What's going to happen if we increase the partial pressure of hydrogen gas? Now, before we answer that question, I want to mention a few things. When speaking in terms of a reactant or a product that's dissolved in the aqueous solution, the term partial pressure doesn't apply because it's not a gas. However, we can describe it in terms of its concentration. But when dealing with the gases, you can talk about it with reference to partial pressure, since all gases exert some level of pressure. But you can also talk about it in terms of concentration, because in a reaction vessel, there's going to be some number of moles of a particular gas in a certain volume. The reaction vessel will have some amount of volume to it, either a 2-liter vessel or a 3-liter vessel. So you can describe a gas in terms of concentration and in terms of partial pressure. Now, as we introduce more hydrogen gas to the reaction vessel, the concentration of hydrogen goes up, and the same is true for the partial pressure of hydrogen. Both goes up. So the effect of increase in H2 will have the same effect as increase in the partial pressure of H2. They will cause the reaction to shift in the same direction. So whether we're increasing the concentration of H2 or increasing its partial pressure, the only way we can achieve that is by adding more H2 to the reaction vessel. So what's going to happen as we add H2? As we increase the reactant, the system is going to try to decrease the reactant. It can only do that by shifting toward the products, where the products will go up and the reactants will go down. So it's going to shift to the right. And as it shifts to the right, it's moving away from CO, CO being a reactant. So this time, CO is going to decrease in value. So that's how we can cause the concentration of CO to decrease. We need the reaction to shift to the right away from the reactants, causing this to decrease while the products go up. So answer choice C is the correct answer. So here's a good way to remember this. In a reaction, we have the reactants on the left, the products on the right. Now let's say the reaction is shifting towards the right. Notice that it's shifting towards the product side. Therefore, the products should increase in value. And it's shifting away from the reactant side. Therefore, the reactants will decrease. So that's a good way to remember what happens there when it shifts to the right. When it shifts to the left, notice that it's shifting toward the reactants. So in whatever direction equilibrium shifts towards, where the arrow points, that's what's going to go up. So as it shifts to the left toward the reactants is going to go up in value. And it's shifting away from the products, so the products will go down in value. So that's a good way to remember what happens to the reactants and the products when the system either shifts to the right or to the left. Now let's look at answer choice D for the sake of understanding. What happens if we were to add an inert gas, such as xenon, to the reaction vessel? Neon is also an inert gas. So this can be true of any one of the noble gases: helium, neon, argon, xenon, krypton. They're all inert gases. What's going to happen if we add an inert gas to this reaction? So if we were to introduce xenon, xenon doesn't react with any of the reactants, nor does it react with any of the products. And it's not in this reaction. It's not included in the equilibrium expression. Therefore, the introduction of this inert gas will have no effect on the position of equilibrium. The reaction will not shift to the right, nor will it shift to the left. So C is the correct answer for this problem. Number 3. Which of the following statements is true if O2 is removed from the reaction vessel? So if we decrease the concentration of O2, what will the system try to do to the concentration of O2? It's going to try to do the opposite. It's going to try to increase it. Now, in which direction will the reaction have to shift in order to increase O2? Now O2 is a reactant, so in order to increase the reactant, it has to shift towards the reactant. So the reaction has to shift towards the left. As it shifts towards the left, let me put this here. The concentration of all reactants will go up when it shifts to the left. So SO2 will increase in value, and O2 will also increase in value, which is what it's trying to do. Now the reaction is shifting away from the products. So SO3 is a product. Because the reaction is shifting away from it, the product will go down in value. So now we could find out which statement is true and which one is false. So number one, the reaction will shift to the right. That's false. We know it's going to shift to the left. So statement 2 is true. The concentration of SO3 will increase. That's false. SO3 is decreasing because it's going to shift away towards it. It's shifting away from SO3, so that's why it's decreasing. And number 4, the partial pressure of SO2 will increase. That's a true statement. As the reaction shifts towards the left, towards the reactant, SO2, being a reactant, will increase in value. So both the concentration and the partial pressure of SO2 will increase. So only statements 2 and 4 are true. Therefore, answer choice D is the correct answer. Now let's move on to our next topic. Let's say we have A reacting with B to produce C, and everything is in the gaseous phase. What's going to happen if we increase the volume of the container? Will the reaction shift to the right, or will it shift to the left? Now, if we think about the ideal gas law, PV is equal to nRT, if we divide both sides by V, we get that the pressure is equal to nRT over V. Notice that volume is in the denominator of that fraction. That means that volume and pressure are inversely related. If you expand a container, if you increase its volume, the pressure is going to go down. And that is the total pressure of the system. Now, what's going to happen if the total pressure decreases? Well, the system is going to try to increase that total pressure. Whatever change you impose on the system wants to undo that change. So if you decrease the total pressure of the system, it's going to try to increase it. Now, in which direction does the reaction have to shift in order to increase the total pressure? Should it shift to the left or to the right? Now, notice that we have one gas molecule on the right side, but we have two gas molecules on the left. In order to increase the total pressure, it needs to shift to the side with more moles of gas molecules. So we have 2 moles of gas molecules on the right per 1 mole on the left. So it's going to shift to the left side because there's more moles of gas. And by shifting to the left, it's going to increase the total pressure. Earlier we said that as we increase V, the pressure decreases, since V is on the bottom. But N is in the numerator of that fraction. As we increase N, the pressure increases. So in order to increase the total pressure, we need to increase the total moles. So when the system tries to increase the total pressure, it's going to go to the side with more moles of gas. There's a direct relationship between N and P. Now let's consider the reverse situation. If we were to decrease the volume of the container, the total pressure will increase. Now the system will try to decrease the total pressure. So in order to decrease the total pressure, it needs to decrease the number of moles. There's a direct relationship between N and P. And to decrease the number of moles, it has to shift to the side with less moles of gas. That is towards the right, because there's less moles of gas there. Now let's understand more about this, because we describe this in terms of the total pressure inside the container. But let's talk about it in terms of the partial pressure. So we're focused on the second situation. As we decrease the volume, the total pressure increases. That means the partial pressure of every gas increases. The partial pressure of A goes up, the partial pressure of B goes up, and the partial pressure of C goes up. Now what happens if we increase the partial pressure of A? If you increase A, the system is going to try to decrease it. It's going to try to bring it down. And the only way that's going to happen is if the system moves away from A. So it's going to shift towards the right. Same thing for B. If we increase the partial pressure of B, the system is going to try to decrease it. So it has to shift away from B to decrease the partial pressure of B. As we increase the partial pressure of C, the system is going to try to do the reverse. It wants to decrease it. So it has to shift away from C, that is towards the left. So notice that we have two arrows going towards the right, but only one arrow going towards the left. The net effect is that these two is going to win over this one. So 2 against 1, the net result is that the reaction is going to shift towards the right if we decrease the volume.